Welcome to section 6.1.1 Dimensionality Reduction Practice. So let's launch the notebook, Jupyter Notebook from Anaconda, which I already have launched. And let's open the Dimensionality Reduction notebook. So as we discussed in the lecture, there are different methods of dimensionality reduction. Two of those methods we will cover in this exercise. So first, we will discuss principal component analysis. So let us load some example data and some libraries. In scikit-learn, there is principal component is part of a library, a module called decomposition. It's a kind of matrix decomposition approach, whereas linear discriminant analysis is part of a module called discriminant analysis. So let's begin with loading iris data, the data set, and this data set contains 150 samples and with four-dimensional data, four features, which are actually different features related to those flowers, and one target variable, one-dimensional feature. So in the first step, we will define principal component analysis. As we discussed that principal component analysis, and let me split this for your view. So principal component analysis, when we will define principal component analysis, there will be actually many features, so many other parameters. If you will write something like that, and you put shift tab, the quick signature tells that we have number of components, copy, whitening of data, which solver to use, tolerance, and so on. I think the most important for now is the number of components, number of principal components. So we have four-dimensional data. So let us define to declare an object with two principal components. And in the next steps, then let's fit this to data. And I will split it again for the view. So when we say PCA.fit, so it will fit a principal component transformation on X. And that transformation we will call PCA fitted. If you will shift tab again, then you will see that this is actually an object of type PCA. So PCA is an object here in scikit-learn. Of course, it has also now a fitted PCA now, and it has some functions that we can apply. Do you notice something? We have X and we have Y, but PCA is an unsupervised dimensionality reduction method, and that is why it cannot use anything from the target variable. So once we have learned the transformation of the data itself, let's transform original X into new PCA space. Let's call it XR, basically a reduced dimensional space. So the function transform in the PCA object will take this data X and project into new dimensions. So as you can see, it took 150 samples in four-dimensional space and it translated them to 150 by two-dimensional space. So we also discussed that the principal component analysis is trying to find out the first principal component will determine the dimensionality with the maximum variance. The second will be the next one, and the third will be the next one. We have two PCAs. So there is a parameter after fitting the PCA object has a parameter property called explained variance ratio. So this will actually involve that how much is the variance that is explained, how much variance in the data is explained by each dimension. These values should sum up to 1 if we have used all the PCAs, all the principal components. So here the first component explains 92% variation in the data, which is already pretty high. And the next PC dimension determines 0.05. So these are, if you sum them up, this is nearly 98% explanation of the data. So the first two dimensions already are good enough for 98% of explanation of the data. So exercise for you is to then determine the explained ratio for third and fourth component, and what will happen and how many features do the PCA fitted has. PCA fitted is our now an object of feature transformation. So how many original feature it is using? Well, you should look into documentation and you will see there is actually a variable that will explain. Thank you very much. Next, I would like to start linear discriminant analysis, which is also a dimensionality reduction method. However, linear discriminant analysis is a supervised learning method, as we discussed in the lecture. So the method is pretty simple. Inside the scikit-learn, we have a module that contains linear discriminant class, and if I would just press the shift tab to look into the documentation, or shift double tab to look into a little bit more detail, or shift 4 tabs to actually bring this here. So you see linear discriminant analysis, it has as an argument a solver. There are different types of solvers, shrinkage, priors, number of components. This is what actually we will be using here, tolerance to stop, and so on. So you can read the documentation here. For this exercise, let's begin with the two components, similar to like PCA, and we will fit the data and then transform that data. So like we had LDA fitted, so we can also make it similar to PCA fitted. So let's call the LDA object and we fit it into x comma y. So you see there is a difference here. Let me start. So LDA fitted is containing two information, x and y, because it will make use out of that. Next, we transform our data, original data, into, and let me split this cell. So now we use our LDA fitted to transform the x, similar like we did in the original case. So just for your fit, okay. Now we transform data into a new data set, which is this case reduced to R2. So similar to LDA, PCA, LDA also has an explained variance ratio by its components. So here you can see that if we try to find out the explained variance ratio, the first two components already basically contains all the 100% variance of the data. So you even don't need a third or fourth component, unlike PCA. So this is an example that how LDA perform better than PCA, because it makes use of information of target variable. Of course, it is only applicable when we already have the target variable. Of course, it's also a bit more complex. However, it could be applicable. There could be situations where LDA provides a very big advantage over PCA. Then there is a little bit part of the code. There we will just plot and what we have discussed, and we see actually the visualization of the data. This is from a sklearn website. So we have what we are doing here is that we are actually using both our XR2 in the second one, and in the first one we are using XR. So you remember XR was transform data by applying PCA, and XR2 is transform data by applying LDA. You don't have to remember this code entirely. This is more for visualization purpose. However, it uses matplotlib, and you can actually make changes for your own convenience. So the first figure is actually PCA for iris data. So this is how the data is now into this new two-dimensional reduced space. Of course, three classes looks different. Also looks different. However, the same data when applied with LDA, which is a little bit, which is more supervised, you can see that the two classes of on the right hand side, they are now more separable compared to the PCA. Yeah. So you can also make more changes to this exercise. Thank you.